Actually, the one thing that I'm doing that I'm hoping many of you have already taken part in is that the IEEE International Symposium on Information Theory is going to be held in Athens this summer, and I'm one of the general co-chairs. And our own, or your own, Greg Warnell is one of our plenary speakers, and we're very excited to have him on board. I actually have very strong memories of Greg when he interviewed at Princeton, and I was a grad student. He didn't wear a tie, and his slides were handwritten, which we were right at the beginning of sort of, electronic production of slides, et cetera. And this to me just seemed really radical. But I understood why he handwrote them, because they were physically some of the most beautiful slides I had ever seen. So I don't know if you have any in storage, but they're just gorgeous. He has lovely penmanship, by the way. So let me start. I had no idea I was the first one, so thank you all for coming. I know it's the first day of the semester, very busy, so thank you for being here. I'm very excited about this work and all of the things that have come out of it, and hopefully I will do it justice. Because I usually get excited during talking, I forget, so I'm going to do my thank yous first, because I am, of course, very indebted to the students and postdocs in my group. This is sort of by academic seniority. So Praneeth is a postdoc in the group, and Lei is one of the new students. Also quite grateful for the various organizations that have sponsored our work. So let me start. You probably got a little sucker punched into coming to this talk because I wrote the abstract in a very general way. But I want to tell a little bit of a story as to how this work came about. We're all very interested and active in applying learning theory to lots of different problems, but our solution to this particular problem would not have happened if we were not wireless communications engineers and worrying about specifically how to optimize wireless networks. So it's okay, I think, to still be an applications person. And sometimes it will allow you to make a contribution in one of these new spaces by trying to bring things together. So this is what I want to try to do. And this is a very canned, contrived example because we went out of our way to make it a little bit complicated, right? So you see I have multiple transmitters. They each have a battery, so we have energy harvesting going on. There's some relays in there. There's interference, et cetera. And the question we want to ask is, well, how should we optimize this system? What's the policy we should design? And in particular, what does that mean in this case? It could be something as simple as, should the transmitter transmit at all? Is it worthwhile? And should it use high power, low power, et cetera? And so these are the kinds of control decisions that we are trying to determine. And as we do in these problems, we want to optimize some metrics, some kind of cost in order to make these choices. So there are a number of challenges that we have to overcome. One is that I'm not actually interested in this toy example with a small set of transmitters. I'm actually interested in very large networks. And this is showing the growth of cell phone accumulation, if you will, over the years. And it's getting bigger and bigger. The other thing that's become challenging about our networks is that the nodes have become very heterogeneous. So we can't treat them as entities that have the same capabilities. They're actually individual. And then on top of that, we also have evolving complexity of the nodes. And this in a way is a good thing for us because it means the kinds of computations we can do on an individual node, we can do many more of them. And I have this picture here in particular because I actually carried one of these. This is one of the early Nokia cell phones. It was like a 6-pack of Coke. And my first research experience was with a collaborator of my father's in Finland, and he was like the Nokia chair and eventually became head of research there. And so he would bring toys home. And so I got to carry this around, when I would go visit the family. And of course, things have changed quite a bit. Still, I think they're going in the wrong direction. I wish my phone was smaller. As I said, it doesn't fit in my pocket, but that's another challenge. Okay, so networks are getting larger, the nodes are getting heterogeneous, and they're becoming more complicated. And so we want to ask, how do we optimize and design these kinds of networks? So, because of course it's very fashionable to be in machine learning, I tell people I do model-based machine learning, which is what a lot of statistical signal processing has been for decades. But if anyone gives you this speech or this line, as I have just done, the question you should ask is, that's great, what is the model? Like if you're talking about model-based machine learning, what is the underlying model? And we're going to use a very classic model here. I want to model behaviors in my network using Markov chains. But of course, since we're also doing controls and actions, I'm actually going to have a Markov decision process. And there's a lot of different randomness in the environment, which could be noise, channel conditions, behaviors of other nodes. All right? But this is my building block, a Markov chain, and then on top of that, controls and actions. And if I think about this wireless communications problem, I recognize that the large Markov chain or collection of chains that I'm going to create actually have a lot of structure because they are from this engineered system, all right? And so these are some of the basic building blocks that come up a lot in terms of sub-Markov chains, if you will, in my wireless system. So I can have random walks, I can have backward counters and forward counters, and when I concatenate all of these things together, I'm going to get a super chain that is not completely arbitrary. It has this structure to it. And this is a structural property or that we want to be able to exploit. Now in this concatenation, I'm going to introduce coupling, and this is what makes design and control hard, because if there wasn't coupling, I could essentially do optimization on a series of individual axes and come up with optimal controls there and just club them together. Okay? So I've been talking about these kinds of descriptions for wireless networks for a while, and especially because we all come from different perspectives, there's often this little bit of confusion, so I want to make sure we don't have that, which is my graphs are very large, but they are logical graphs. And what do I mean by that? Every single node, right, in this chain corresponds to the state of the entire system, all right? So it's a particular value of some vector. So it's like, you know, Kunal's got 5 packets in his buffer, I've got 15, Xander's got 12, so I have everyone's buffer states collected. I have everyone's channel states collected. I have everyone's, you know, whatever possible feature we're looking at, they're all collected together. So each node is not a user. Like, this is not a sensor network where I'm talking about neighbors that are physical. I'm talking about neighbors in a graph, and that's a logical concept. Now, because of this, sorry, we just went over this, so this is my little cartoon. Because of the fact that I'm collecting all of my attributes together, it's very easy for me to have state explosion, right? Because once I start putting this all together, if you look at all permutations and combinations, things get large quickly. So if I have a simple system, 2 users, a length 5 buffer, 4 retransmission states, if I'm doing some automatic repeat request type of thing, I get 1,700 states. So this is a challenge, right? Because on the one hand, I told you I'm interested in large networks. I'm now describing the behavior of the entire network simultaneously, and you know, I now have a very big graph that I need to deal with, all right? And so there's a series of questions that I want to walk you through, which goes along with this story of how we came to this notion of so-called digital cousins. And so the first question that we asked ourselves is, can we compress these graphs? Is there a different representation of smaller dimension that will assist in our ability to design optimized controls and policies? Okay? And so a simple way to think about graph compression, and this is not what we're going to do, but it's a competing strategy that we've investigated, is you figure out some notion of closeness in your graph, pick your metric, and then you aggregate nodes into like a virtual supernode to correspond to those states. So clearly I'm reducing the number of nodes in my graph. It's a smaller problem, I can do my optimization, and then use a process called lifting to take the control back up to the full graph. And this is a very beautiful piece of work done by Sean Mine when he was still at the University of Illinois in terms of informed strategies for doing this. And basically they do state aggregation by optimizing KL distances, right? They're trying to get the behavior, I mean, essentially a Markov chain or a graph is describing the behavior of a discrete state random variable with memory, right? And so you can see as you do this compression, you can look at the closeness between the statistics of the compressed graph and the uncompressed graph. Of course, we don't have just the graph. We also have actions that we want to take. So this is something to remember. And I just, again, want to emphasize that we are looking at these so-called logical graphs. Okay, so let's do a little bit of math. I know this is a community that can handle it, but I have de-equationified most of the slides. If you want to see them, they're hidden, but they're there. So my Markov decision process is described by this 4-tuple, all of the states, all of the actions, the costs associated with them, and some probability transition matrix. And in fact, as we design new controls and policies, we're actually changing the underlying probability transition matrix, right, in terms of behavior of things. Okay, so again, my policy, which I'm going to call pi, could be any set of actions. I've given you example actions, transmit, idle, power, etc., whatever are the choices that my nodes can take on. So what we typically want to do is design a policy to optimize some aggregated cost function, which we're going to call the value function. You can look at this in a finite horizon way or an infinite horizon. We're looking at infinite horizon. And you want to pick the policy that's going to optimize this objective function. The form of it isn't super important for what we want to talk about today. All right? And of course, as I take different actions, it's going to impact other users or nodes in the system, and it's going to change behaviors. All right? So this is something that people have been worrying about for a long time. And because this is often, you're solving a dynamic program, essentially, this is computationally expensive. People look at different strategies to reduce complexity. And so there's this notion of these iterative strategies, which are provably good under appropriate conditions. And you have this sort of, policy evaluation step and a policy improvement step, right? And they're kind of straightforward to do, and there are lots of clever implementations of these kinds of schemes. And as I said, under the appropriate conditions, you can show that this iterative updating scheme converges to the optimal policy, but there's a complexity that goes with the size of the graph, if you will, okay? And so what we want to do, and this, I actually don't know what the original citation is, but since I'm at MIT, maybe somebody does know, but it's in one of Bertsekas's books on dynamic programming, which is the notion that you do something very simple. You all learned it in linear algebra. We're going to do a projection of the value function, right? So if you project in the appropriate lower dimensional space, you can solve everything in that lower dimensional space and then again lift back up. You lose some interpretability in the sense that, what does the lower dimensional space mean? I don't have this nice notion as I did in state aggregation where you can club things together and it has sort of an interpretable meaning, but it's a useful strategy. And the hard part here, which is carefully sidestepped in the Bertsekas text, is how do you pick the subspace that you're going to project onto, right? And this is actually where things got hard and interesting. What is the right projection to do? And so the first thing that we played around with, and this is work with Andrea when she was at Stanford and Marco when he was a postdoc that was shared between us, Stanford and USC, we looked at centralized random projections. And we were looking at this kind of approach because this was sort of in the early days, if you will, of compressed sensing. And it just seemed like, could we use compressed sensing ideas and apply them to graphs? And of course, the answer is in the affirmative. And so, again, like in classic compressed sensing, you have some signal that you believe has a sparse representation. You apply these randomized projections in order to essentially give you the ability to see mixtures of these unknowns, the unknowns being small, right? And so I want to learn X, I have this observation Y, but what I really want to understand is what W is, and if I apply this randomized projection phi here, it gives me good properties that allows me to recover my unknown X with high probability, right? And a way in which this is often solved, and I'm probably telling you things that you already know, is to look at this particular optimization here, where you're essentially minimizing a mean squared error type cost function, but you have this penalty term that encourages sparsity in your solution X, right? So this is what everybody was doing in problems like this. Now, as I said, there's not that much math, and these equations are actually trivial, but they show us that we can essentially look at the Bellman residual, right, which is the expression that's being solved by this policy iteration, and I can rephrase this so that it looks a lot like a modified squared error. And then if I add in a penalty term, I can use lasso-type strategies in order to recover this signal x. And what I'm trying to do in this particular problem is essentially learn my value function by taking observations. I have memory in the system, so things are a little bit different. But it turns out that it works very well. So this is now, I mean, perhaps it's embarrassing that I'm showing you a plot from a 2010 paper, but we've been worrying about this problem for a while. And what you could see is that by using this sparse approximation and compressed sensing, we could learn the underlying value function using many fewer observations than sort of standard Q-learning, which was the comparison point that we had here. And this is because, of course, in Q-learning, I essentially need to make sure I'm visiting all of my states a sufficient number of time in order to get an estimate of that underlying probability transition matrix in order to learn this function. And so we did a scaling law analysis in this particular work. And you can sort of say, well, how many observations do I need to take in order to learn the value function with high probability? Because there is correlation in my observations that are induced by the probability transition matrix, I actually take a little bit of a hit. If you can just pattern match between this expression and this one here, you see that there are some extra terms in there. So I take a loss, I need more samples, but it works pretty well. Okay, so we did this centralized case. So then we asked ourselves, can we decentralize the approach? And this is work with another postdoc who's was at Purdue and is now at Arizona State. And I'm not going to go into too many details here, but I just want to emphasize that once again, I have a network problem. It's a very different network problem. Here we were looking at cognitive radio, and we were trying to understand how to optimize the behavior of these secondary agile users. And so what the secondary users are trying to do is figure out what frequency bins in which they should communicate by trying to learn the behavior of the legacy users and their occupancy. So visually, this is a very easy to explain. So BK here is a vector of occupancy, so that's what the legacy users are doing. And UK is trying to figure out which spaces are empty, if you will, but these are all also evolving as Markov decision processes in parallel with this other process that I have. And what you want to make sure is that, I'm using up as many opportunities as I can. So in this first example, this is a good control because I'm essentially using all of the opportunities that I can. But in this second example, I have collisions, right? If I try to use, if the gray boxes and the red boxes overlap, then we have collisions. We also don't want any white boxes because that means you're not taking advantage of the full opportunity that's available to you. And so the short story of this is that we could do decentralized projections and form essentially a dynamic version of the compressed sensing problem. And what falls out, again, is something that looks very much like the classical lasso optimization that you want to do, okay? And we also designed a new sparse approximator for this particular case that works pretty well. Okay, so this is my gentle introduction, right? Like these are the kinds of problems we were worrying about. This is sort of the landscape before we changed gears a little bit. In everything that we did before, to kind of take advantage of the machinery that was afforded to us by the existing compressed sensing results, we looked at these randomized projections, right? And there were statements we could make, but in a sense, they were not really tailored at all to our specific problem. And I started out by telling you there's a lot of structure here. So in a way, by not designing the projections intelligently, we're losing a little bit, okay? And so the question is, can we optimize projections? And this is something that we've been working on for a while here. And so the tool that we wanted to use, again, it was of the moment. Graph signal processing was being applied to a lot of sensor network data where there was a physical graph, that there were observations at different locations, and you could describe those collections of observations through a graphical structure. And essentially what you're doing is think about all of the analyses that you do on time series. Okay, so we're going way back to undergrad, right? So you can do things like sampling and filtering and signal reconstruction, et cetera. Now I want to do this essentially in a multi-dimensional way, looking at these graphical structures. So you can reinvent all of those things, right? And so the hope was that if you think about this, I could pose this as a sampling problem, which is which nodes should I sample? And that's a way of doing a graph compression, right? And if I pick smart nodes, then I can reduce the size of my graph by simply a subsampling of the nodes and do all the processing there. That did not turn out to work that well, so we're not going to talk about it, but this is where we started. Now, again, all of these things we can reinvent, right? Frequency decomposition, sampling, filtering, and sort of the key building block was this notion of a graph Laplacian, which is a simple function of the adjacency matrix of a graph. Now, one of the challenges that came up, and it seems like it wouldn't be a big deal, but we spent a lot of time worrying about it, is that at the time, most graph signal processing assumed undirected graphs, right? So everything was bidirectional, reciprocal, etc. And this is something we definitely do not have in my wireless network graphs, right? My buffers cannot be filled arbitrarily 5 to 4 to, they go in a very specific direction, packets come in, packets go out. And so this turned out to be a very challenging problem. And I feel a little silly because on the one hand, there were solutions out there. Jose Moura and his group at Carnegie Mellon have beautiful graph signal processing papers on directed graphs by using Jordan forms, right? Now, I don't know how you were taught Jordan forms, but when we teach it, it's a little hand wavy, right? Like, we're going to go through some toy examples. You can visually see how to construct your Jordan form, but I'm not going to give you a systematic strategy by which you can compute these. And it turns out to be a numerically very hard problem. So I suspect even now, N years later, there are still people worrying about numerically efficient and stable methods by which to compute Jordan forms. And since we were not numerical methods people, whenever we plugged our problems into MATLAB, they would just break, right? So you're not going to see any Jordan form results because they just worked terribly. And understanding how to apply it better is something that we worried about. So for the moment, believe me that our challenge was to figure out smart ways of symmetrizing our underlying probability transition matrices. And note that we have a collection of probability transition matrices because they are action dependent, right? So depending on the actions you have. So we're actually looking at a tensor problem here, not a simple one matrix. So the first thing that we had tried actually, because we ran into this in that early paper, is we did something very naive, which is what's the best symmetric approximation of a matrix? Well, it's itself plus its transpose divided by 2. Like that satisfies a simple optimization problem. And actually, in this paper, it worked pretty well, right? It didn't work perfectly, but it worked pretty well. So we started on this hunt, trying to find smart strategies by which we could symmetrize this matrix in a meaningful way. And so one of the things that popped up in I think it was a paper on like social networks or something like that, and it was this bibliographic symmetrization, P transpose plus P transpose P. And this is a very interesting symmetrization to do. And we have reverse engineered why it works well in terms of an argument, and we'll come to this, but we tried a lot of different strategies. One of the things that we also tried is assuming that you want to look at the best undirected graph approximation, we looked at matching value functions across trajectories. This was computationally extremely expensive because, if you look at short trajectories, you're not capturing everything you need if you look at long trajectories. So it was the most expensive thing that we could do, but in the end, it didn't work that well. And so if you take a look, so here's a simple example. So it's small. I actually only have one user, if you will, but it helps to visualize things, where I have a channel state and a buffer, and I'm just trying to figure out, should I transmit at all, right? So my optimal policy looks like this here, and again, I have the buffer state and the channel, so basically, I measure these two things depending on the value. This is like a table, and I decide, am I going to transmit or not? And this is the cost function that we came up with. And if you look at this particular strategy, so policy iteration, of course, is optimal. It gets me very good results. If I do my vanilla symmetrization, it doesn't do very well. If I look at what seemed like a very smart trajectory matching strategy to figure out the best undirected graph, it also doesn't work very well. And random, doing something random doesn't work at all. Interestingly enough, this bibliographic symmetrization works very well. So how do we argue our way through this? If you take a look at this expression, what it's essentially doing is any strong outgoing link is strengthened, right? And any strong incoming link is strengthened through these operations. And I preserve symmetry in the doing of this, okay? And as I said, Jordan forms just failed completely. So we realized, again, looking through the literature, and I have to say Talha is just amazing at finding papers. So I think this is some physics paper maybe, but you can actually generalize this symmetric proxy, all right? So this is good because it captures these strong incoming and outgoing links, but it's only kind of a one-hop measure, if you will, all right? And we're interested in behavior across multiple hops through this graph because we will get better performance. And so you can do this generalization. Oh, actually, no, I think it's another social network paper, which comes from this work here. Again, how we found it, I have no idea. And you can see that you can take this symmetrization process to multiple orders, all right? There's a formula, it's straightforward. It preserves symmetry, so these L matrices are now symmetric. And what I can do is use these L matrices as if they were probability transition matrices, and I can design my projections based on these matrices, all right? And so that's what we're going to do. And so there are a number of nice technical statements we can make. We can show that these matrices are approximately block circulant, and that's very useful for reducing complexity in computation. So we can come up with a low complexity decomposition that then leads to low complexity optimal policy design. And we can also come up with a method by which we can tell you what the optimal order is, right? So it is not monotonic, like as n gets bigger, it's always better. Each problem is a little bit different. And so this is something we can do. And again, just to show you, like, you can see that the approximate block circulant nature right here. And so in the case, and I should have emphasized this before, so far we've been assuming that I know what that underlying graph is. I just don't know what the optimal policy is, and it's expensive to compute. So I take these descriptions, I do eigenvalue decomposition on the L's, and then I pick the dimension, if you will, that I want to project onto. I do all of my policy optimization in the lower dimensional space, and then I lift back up. One of the nice things about this block circulant property is that I can use this to do fast estimation, right? So in a Q-learning type environment, if I don't know what this is, if I know it has the structure, I can combine transitions to get good estimates of the blocks and then use that to percolate it throughout the entire matrix. Okay, so just to give you a feel for like, oh, how well does this work? Let's go back to my complicated canned problem because it has a lot of things going on. And let's see how well we do. So I'm going to look at a variety of symmetrization strategies or graph compression strategies. I have my vanilla P plus P transpose. I have this work that I've just been talking about. There's also, interestingly enough, a lot of different strategies out there to try to figure out how to do graph reduction. So Talha found a number of these, and then this is the beautiful paper by Sean Mine, which is this state aggregation strategy. Also incredibly expensive and hard to do if your graph doesn't have structure, right? And so they have, so it's computationally expensive. So we are looking at average policy error here as a function of the network size, and this is the number of nodes in the graph, okay? And I want this policy error to be small, right? So I'm comparing to the optimal policy. And what we see is that, our proposed strategy is not just computationally cheap, it's also giving us the best policy error of all of these different strategies, okay? And I'll argue that part of why we're getting these gains is because we're doing our projection in a way that's exactly tailored to the problem that I want to solve. I'm taking the underlying structure of the wireless network explicitly into consideration, whereas these strategies are not taking advantage of those properties. I'm not going to show it, but I also have much lower runtime complexity. So this is much faster. I'll show you some runtime figures later. Okay, great. So this is a case where I know what the underlying probability transition matrices are. Okay, now what do I do if I don't know them? All right, and so we did what lots of people do, right? We adopt a Q-learning type strategy where we're essentially, learning this proxy cost function, the Q function, and making decisions based on this. And of course, you can do, there's so many variants of Q-learning, it's actually kind of breathtaking. And we've looked at quite a few of them. So one of the things that we realize is that, exploration in these reinforcement learning strategies is expensive. And so a lot of energy has been devoted to trying to improve exploration, which is essentially your learning process, right? And so we'll look at a number of these, but I just wanted to emphasize that, many people have looked at this. So this is the new stuff. Can we improve exploration? Is there something intelligent we can do, recognizing where my graphs are coming from and what we're trying to optimize, right? Which is these policies where taking the memory of the system into consideration is important, right? I have this memory due to my Markov chains. Okay, so I want to do something that is akin to a digital twin, except that it's not, which is that we're going to create synthetic systems that are going to run in parallel to my real system, and we're going to learn as we go on everybody, if you will. And the synthetic systems are going to be structurally related to my true system, and they're actually going to have a significant impact on my ability to learn. I'm going to learn much faster, okay? So this idea of combining solutions, right, this ensembling, this is not a new idea. And again, if you look, there's an amazing number of strategies for ensembling solutions. And so what do I mean by that? So imagine, you're going to see this picture a lot. So this is to describe my actual system. Some graph, some Markov chain, there's actually a bunch of them, but this is one here. And maybe I run different forms of Q-learning on the same system, right? There's strategy one, which is going to give me, say, we've been doing tabular Q-learning. So I get one table from strategy one, I get another table from strategy two, and then I come up with some clever way of combining these to get a single Q table from which I'm going to decide what actions I'm going to take, okay? And people also do different initializations. That might be the only difference between these different Q-learning strategies. And you, again, combine them, and you get something that may or may not be optimal. That's part of what you try to show, that it works well in simulation, and see what kind of technical statements you can make, okay? The claim that we're going to make, and I should probably temper this, is that the notion of having multiple systems is not well studied. So let me emphasize what I'm going to do here, all right? So I have my wireless network problem. Okay, so things are actually connected. I didn't tell you about this co-link symmetrization because it was fun. I also need it, because what's interesting about it is that using this co-link method, I can come up with these different orders, right? And clearly they're structurally related to each other because they're all a function of the same P matrix, right? And each of these L matrices captures, well, I think of it as multi-hop relationships, right? L squared is kind of capturing 2-hop relationships, L cubed, 3-hopped, et cetera, et cetera. Okay, so I'm capturing these multi-hop relationships. And so what I'm going to do is, my original graph, this P matrix, it's unknown. I'm going to use some strategy, usually maybe the vanilla strategy, to learn P hat. And then I'm going to use P hat to create L hat squared, L hat cubed, et cetera, right? So these L's, these are my structurally related synthetic systems. So I'm going to take a little bit of a computational cost here because I want to run L2 and L3 in parallel to my real system, okay? And so now, as opposed to what had been done in the past, I'm going to run these three systems at the same time. Real ones happening, I'm collecting data, updating P, etc. And I'm also running the fake ones. Each of them is going to have Q-learning on them individually, all right? And then I'm going to fuse them to create my optimal policy, okay? And in a way that this works is, I have to be honest, it's a little bit surprising, right? But it does work. And what's all the more surprising is that I'm running these synthetic systems on estimated graphs. So I know that they're imperfect, okay? And again, you can, use some strategy. So this is my ensemble policy. I have individual policies for each of the synthetic systems. And I end up doing a weighting on the different systems before I do the policy combination, because I kind of want to get a sense of the utility, all right? So one of the things we're going to cover is the fact that, let's say I knew P perfectly, right? I knew all of the underlying transition matrix exactly, and I still created these synthetic systems. Their optimal policies are not identical, even in the case where everything is perfectly known, right? But what is useful and provable is that they are not too far from each other, all right? And it's that closeness that we're going to be taking advantage of. So again, we have a variety of strategies, but what I want to underscore is that not each cousin is equally useful and informative. The way we do the weighting is to see how far away everybody is from like the real system, right? And of course, as we move on, the policy is being updated, but that's something that we take advantage of. Okay, so it works great numerically, you're going to see this, but we've been trying to come up with explanations that have interpretability to say, well, why does it work well, okay? So here's one of my analogies. So let's say my goal is to collect samples on a track, right? I don't know if anyone ran track in high school, I did very badly. So you're running around the track, right? And what I can do with my digital cousins is I can obviously initialize them at different locations, right? But I also have runners of different sizes, right? So I'm the black runner right here, taking my small steps. And because those synthetic systems are looking at these multi-hop relationships, I think of them as running at different timescales, right? And think about this going back to your baby analysis of Markov chains, right? P squared is the transition matrix for 2 hops at a time, right? P cubed, etc. And in fact, when I do these multi-scale things, I'm designing policies for this new system that is making these multi-hop transitions, right? It's not transitioning one at a time. And so if we all start at different places and are taking different steps, you can see that we are going to more effectively sample the track than with my one small me, taking my small steps along the track, okay? So we're getting better sampling of this Markov chain, basically, and the trajectories. Okay, so let's do some numbers, all right? So I'm going to go back to my canned example. I should have emphasized this before. I am looking at, I'm discretizing my channels. So they're essentially, an M-state Gilbert-Elliott channel. So everything in here is discrete, all right? And yeah. Okay, so some very interesting observations. I told you that I had this weighting system to try to balance the informativeness of each of the chains. So not, there is a favorite child here, right? Like not everybody's equal, or I should say favorite cousin. What's interesting is that the weights converge, all right? And I'm not, as I told you, I'm not monotonic. Like W4 or the 4th chain is not more important than the 3rd chain. And so I have 3rd is more important than 4th, which is more important than 2nd, all right? 1st chain, always the most important, always, okay? Which of course makes sense because that's the chain that we want to design for, right? Okay, so there's a lot of technical statements. Let me just kind of quickly run through some of them because I think they're interesting. So as you saw before, we can prove that the weights converge to constants, all right? We can create upper bounds on the estimation error, and depending on the assumptions we have, The bounds are either tighter or looser, right, as a function of those assumptions. We can show that this sort of error, on average, is roughly proportional to the number of cousins, right? Which, on the one hand, says, well, then you should have the maximal number of cousins possible, because then your error is going to scale according to that. It's not exactly true, because there are some independence assumptions in making that statement that we know don't hold, right? As I create more and more cousins, the trajectories are going to become somewhat correlated with each other, which is a good thing on some level. I told you I could bound the error between the first Q function of the first chain and the others. So I have some notion of their closeness to each other. And as I said here, the optimal policy for these cousins is not the same as the optimal policy for my actual system, all right? And I have a little bit of a conjecture about this. For a general case, not the wireless network case, I can create a partial ordering so I know a priori the relative importance of some of these chains. And as the order gets larger, they become less informative. What's interesting is that it's like the odd chains versus the even chains, that relationship is not as well understood by us. But odds versus each other and evens, we can make strong statements. Okay, so again, here's my conjecture as to why I think things are working. And this is an imperfect set of slides, so if you have an idea at the end of this talk of how to do it better, please let me know, because we've tried various ways of doing this. So what I want you to think of, so what are these ellipsoids? So these are somehow a representation of my Q functions or my Q tables, right? And it's what I can do with a certain number of observations. So as time goes forward, I'm going in this direction. This was my Q functions at t plus 1, t plus 2. The ellipsoids are like my error balls, right? So as I'm collecting more observations, those balls are getting smaller and smaller, okay? So this is my in real life system, first chain, the one I care about, right? So now I have my cousins, which I'm only showing one because then we wouldn't be able to see anything. Same kind of idea in terms of trajectories of the Q functions, error balls getting smaller. But what you see is that there is much more overlap of the big ellipsoids, and the overlap is getting smaller and smaller as time goes on. So my argument is that at the beginning, as we're learning this system through the Q learning, there's enough overlap of those error balls that the trajectory information that I'm getting for the synthetic systems is actually informative. As time goes on, they become less informative because I do know for a fact that each cousin should be converging to its own system. I've hidden this because there's a lot of algorithmic stuff, but we actually change the weighting, if you will, of the other cousins as we go on, so they become less important because we don't want to converge to them, we just want to take advantage of them while they're informative. So I think this is one of the arguments. And so again, what's interesting, right? So here is looking at the individual learning of those digital cousins, right? And what you see is their policy errors converge to non-zero quantities, right? Because actually their optimal policy, if I run them independently, their optimal policy is not the true policy. But when I combine them in this ensemble fashion, I converge very fast, right, in terms of my policy error, and I get very close to zero policy error, right? So individually, they may not be super useful, but in combination, they are very useful, all right? And so let's do some numerics, and I'm almost done here. And so I realized I had to update this slide, and I couldn't do it right before the talk. So Talha is one of these amazing students who can implement everything. The first time he showed me plots, there were 12 curves. And I said, I don't think we need to compare against 12 different strategies. Let's cherry pick ones that tell part of a story. What we know is that you do better than all of them. So, it doesn't really matter which ones. But he looked at a wide variety of strategies, including ones based on deep learning and other forms of neural networks, all right? So here's, again, average policy error as a function of network size. And first of all, everyone gets worse as the networks get large because it's a more complicated graph that you're trying to learn. We are the brown line down here, vanilla Q learning is up here, and everybody else is sort of in between, all right? I promised you that we would look at runtime complexity. And again, we do quite well, much less complexity than everybody else. The fact that we perform better than a neural network architecture is not surprising. It's trying to build a very complicated function approximator, and it just needs a lot of training data. We're exploiting side information and structural information as given to us by these L matrices. So everywhere I can optimize things, I do, all right? So, you know, I have had people say, don't you worry that neural networks will kill your research program? And I say, never. I work in an environment where we have models and structure, and as long as we take advantage of that, we're always going to do better. And actually, I'm going to understand the solution in a way that I never will for some of these different kinds of neural approaches. So the other thing that's interesting, but not too surprising, is, so this is kind of a repetition of that policy error figure that you saw before. What's changing as we go from left to right is that these are like Erdos-Renyi graphs. I just created artificial ones. This is from a cliff walking example that I think a lot of you probably know about. And this is my wireless network. And the point is, the more structured the graph, the better our strategies work, which again is not surprising. But the key thing is that I don't have to have this structured wireless system in order to apply this digital cousin idea. And so again, we have a greater reduction in policy error the more structured the graph is. Okay, so again, not too surprising. So we're finishing up revisions of the various papers, and so one of the things that, or items that got raised was, hey, you're only comparing to other Q-learning strategies, you need, or variants, you need to compare it to non-Q learning strategies. So again, Talha, amazing implementer that he is, went through and found a whole series of these. The one that I want to highlight is this asynchronous advantage actor-critic strategy, which runs a number of neural networks in parallel, so for the actors and the critics, if you will. And in that way, it has a strong similarity to what we were doing because it's looking at different subsystems, if you will. But because it is a neural network architecture, again, we always win on the side of the training, right? It needs so much more training than we do, so we always have much better performance. So, so let's focus on those two curves here. Now we're pink, and A3C is purple. So for smaller network sizes, it's quite competitive, right, with our strategies. As the network grows, its policy error goes up, but it has a much higher runtime complexity and sample complexity needs versus us, which again, I'm almost at the point where this is predictable, right? And to me, this is the huge challenge with doing research in learning and neural networks now, which is if you have structural information and knowledge, how do you intelligently incorporate that into your design? Because if you're doing a very non-parametric function approximator, you're just throwing away information that you have, right? Which, you never do, or at least we try to teach you to never do. And so I'm sure 5-10 years from now, there's going to be a neural network architecture that beats this because it is effectively exploiting, the site information. Hopefully our name is on the paper, but, I think this is where we're all moving, and, it's great. So there's a ton of stuff to do. So the beauty of any digital twin or digital cousin is that it's completely synthetic. I can do anything that I want with it. I can run it backwards in time. I can send it to unsafe states to understand how my policy evolves, when this unsafe scenario occurs, and I don't break anything, right? I can do random restarts. I can initialize in different spots, and again, because it's synthetic, I'm not going to break anything. So we're looking at a lot of different problems, including decentralization, trying to think about sampling strategies so we can learn optimal sampling on the cousins and then use that to inform how we explore on the real system, all right? There is a strong connection to our LN matrices and graph convolutional neural networks. I feel like this is low-hanging fruit. I just don't have enough people in my group to pick up the fruit, if you will. And then we've also, because of the fact that we're looking at these directed graphs, very interested in causal inference on them. So there's a lot of different things to do. I'm looking here for a postdoc, so if anyone knows anybody who thinks they might be interested in this, please let me know. It's very warm and sunny in California. And so let me just end here by saying, you know, structure is your friend. It's really an opportunity that we should be exploiting. There are a lot of different things we can do. And going back to what I said at the beginning of this, you know, how did we get to this digital cousin idea? It was through looking at these representations of these networks, trying to figure out these effective symmetric proxies, right? If we had not done that, we would not have thought about this notion of running these things in parallel, the fact that I could create these different L matrices at the same time. So I'm sorry I made you take the circuitous path, but I think this is the beauty of research, right? Sometimes you don't know where it's going to take you. And I'm just such a big believer of letting applications drive your designs, right? Because that's, you know, where you can find the secret sauce. So we have this novel, I think, Ensemble Q Learning. I have a project with people who know more learning than I do, Arti Singh and Tara Javidi, and you know, we're all kind of scratching our heads like, can we come up with a better way of explaining why this thing works? And then hopefully use that to optimize the strategy even further. And so one of the things that was on my list of stuff to do is to look at so-called coverage analyses, which is a classic strategy in the RL environment to understand how well, you know, online, offline policies, actor critics, et cetera, work. But we have to redefine what coverage means. And I actually literally sent an email this morning to Hala saying, I don't like how you did it before, you're missing this thing, try something else. So again, very nice numerical results. There are some theoretical guarantees, albeit under some idealized conditions, but you know, that's often the way we start. And I just wanted to highlight these two papers that literally the wireless network paper got accepted this morning. So I got the email, I'm like, great, I can update the slide. It's now public. All right, and I'll stop there. Thank you.